Hello and welcome to Experiment 6 Electrotechnology 1100 and Electrotechnology 1102. Experiment 6 is Kirchhoff's laws and series parallel circuits. The series parallel circuit is provided in the lab document, figure 6-1. We will show you how the circuit has been built and how some of the measurements have been taken. With respect to applying Kirchhoff's laws, you will verify how KVL and KCL apply this circuit when you answer questions 1, 2, 3, and 4. The objectives of experiment 6 is that when you have completed this experiment, you should be able to apply Kirchhoff's current law in a series parallel circuit, apply Kirchhoff's voltage law in a series parallel circuit, design a series parallel circuit to meet specific voltage and current requirements. And so the circuit shown in figure 6-1 contains 9 resistors, and remember that our 1 here and our 9 are in series with the source, and so this branch contains IT. The current IT then divides at this junction right here into currents that will go through I2, I6, and I7. So Kirchhoff's current law should apply at this junction. In addition, Kirchhoff's current law applied at this junction says that I6 plus I7 should equal I8. And then I2 divides at this junction into I3, I4, and I5, so we should be able to apply Kirchhoff's current law here. We should be able to apply Kirchhoff's current law here and say that I3 plus I4 plus I5 plus I8 equals I9 or IT, and that the current goes back to the source. In addition, for any closed loop in this circuit, we should be able to apply Kirchhoff's voltage law. There are several loops that include the source voltage. As an example, V1 plus V2 plus V4 plus V9 should equal 24 volts, and so on. So the first part of this experiment is to analyze the circuit on figure 6-1 using the series parallel reduction techniques to find RT, and then apply the series rules, parallel rules, KVL, KCL, and Ohm's law to find the current through each resistor and the voltage across each resistor. So then complete table 6-1 as you analyze the circuit. And again, you know, this is left as a student exercise. Complete this on your own. Submit your work with your lab. And so, you know, this is good practice for series parallel circuits for this course. And, you know, if you refer to the document, the supporting document, or the last slide in this presentation, you will find that some of the values in table 6-1 have been filled in for you, along with the total resistance, and the idea there is that you can use those as a guide to help make sure that you have your calculations done correctly. So the next step in the lab asks you to measure the resistance of each of the individual 9 resistors, and the following slides will describe some of the measurements taken. Even though in the lab we did measure the resistance of all 9 resistors with the ohm meter, pictures for the first 3 will be shown, and the other values can be taken from a supporting document or from the last slide that includes the tables on page 56. And so we have pictures included for resistors R1, R2, and R3 only. And so here you'll find that we have shown pictures for R1, and you notice that the selector or the multiplier switch is on R times 100, and if you have a look at the needle up here, it's just a little shade less than 3, so we call that 2.95 multiplied by 100, and you got 295 ohms for that. Don't forget that you must zero the ohm meter by shorting the leads together and adjusting the 0 ohms adjust until the pointer is exactly on 0 before you take your first measurement. Okay, so if we move on to R2 now, you'll notice again the selector switch is on R times 100, so we can connect up R2. You can see it down here, green, blue, and brown suggests a color-coded value of 560, and we made the measurement here that we called that 5.7, and 5.7 times 100 and 570 ohms. So the next slide includes R3, and you'll notice that we have moved the selector switch now. So once you move the selector switch up to R times 1000, then you have to connect your leads together again. It's called shorten them out without the resistor, and generally that means that you've moved the selector switch, so when you connect your two leads together, you won't be exactly on 0 here. So play with the ohms adjust button until you're exactly on 0. Generally have to re-zero the meter every time you move this switch. And that has to do with the internal batteries that's in it that are different for some of the different scales. And remember that the reason why we're moving the scale here is that, you know, these meters are generally more accurate if our needle is in the right hand half of the scale, so between approximately 0 and 10 for this ohm meter shown here. So once we've completed the zeroing, then we connect in R3, which you notice is orange, white, and that multiplier there, I guess, is brown, and that has a color-coded value of 3.9 K or 3,900 ohms. And you'll notice that this one is reading quite a bit high compared to that. And we have estimated this to be 4.5. So 4.5 times 1,000, 4.5 K ohms, or 4,500 ohms. And so again, that's a bit high compared to the color-coded value, but we assume the measurement is accurate. Now, the next step is to build the circuit on the orange project board in the lab. And before you connect the power supply, you want to measure RT using the ohm meter. After that, connect the power supply. And then you need to measure the voltage across each resistor and the current through each resistor. Record the values in table 6.2, and those values should verify your calculated values from table 6.1. Now remember that here, you know, we have calculated RT is a little bit higher than the theoretical value because of the color code or the tolerance of the resistors. And in addition to that, that means that at 24 volts, the current will be slightly lower. The current should be, and the voltages should be in the same ballpark as those that you have calculated, but they won't be exact, and that got to do with errors that are introduced by the tolerance of the resistors, by the accuracy of the measuring instruments, and of course there's always a certain amount of human error with respect to reading meter scales and so on. But I mean, the idea here is for the measured values to verify the calculations, and so we expect them to be relatively close. So on the following slides, we will describe the measurements taken. We will show pictures of only some of the measurements. The rest of the values are available again in the supporting document or on the last slide. The completed results table 6-2 has been shown for you. Okay, so the circuit is shown here. And the idea is that we have the circuit laid out relatively closely to what we have in figure 6-1. And figure 6-1 then has the first resistor at the top right here as our 1. Then we have placed our 2 here. Next we have our 3, our 4, our 5, our 6 and 7 in a parallel branch up here, our 8 on the right side, our 9 here at the bottom. And so this terminal and this terminal is where we plan to connect VT, and so that is where we will measure RT. Okay, so the connections using these quick clips are similar to the lines drawn on the diagram for figure 6.1. Okay, so this clip here, these two resistors, left end connected together, right end connected together, so they are in parallel. That parallel branch feeds into our 8. Our 8 is connected to the bottom of this parallel branch. Resistors 3, 4, and 5 are in parallel. The top are connected together, the bottom connected together. Current flows through the wire and through the circuit. Okay, so we have connected our ohm meter, the right terminal to this end, the top end of our circuit, let's say. The other terminal of the ohm meter is connected here. It will measure the resistance of everything that it sees, and so that is the circuit as laid out in figure 6-1. So in step A4, we are asked to measure and record in table 2 the total resistance of the circuit. Now the lead here covers up the meter a little bit, but you can see that the selector switch is on R times 100, which really means that we didn't need to zero it again. Our meter needle has gone, well, maybe a little bit past the right half of the scale here, but the idea is that you know, this part of the scale here, the graduations are really close together, and so it's probably a bit easier to get a measurement right here. Our measurement then for RT, we picked that off as being about 13.4, I think I called that, and multiplied it by 100 and came up with 1340 ohms. And so maybe a little closer to 13, maybe than 13.4 according to that diagram. But in any event, we call it 13.4 and recorded 1340 as that measurement. Okay, so in step A5, they asked us to connect the power supply to the circuit and set it up for 24 volts. And so even though we can't see it very good, the power supply is here, and the LCD display right here shows 24 volts. Now we have connected then the positive terminal of the power supply through this red lead to the top of our 1 right here, and we have connected the black or negative terminal of the power supply through this lead down here to our 9, and so 24 volts is applied to the circuit. Now, our voltmeter is here, and we have connected the positive terminal of the voltmeter to the positive terminal of the circuit or the source. The negative terminal of the voltmeter connected through this black wire here, and even though it goes under the table, it comes back up to the circuit here. So it is across the circuit, so it will measure VT. Now, in order for us to get IT, we could measure the current going into I1, but because we got our voltmeter and power supply connected there, we broke the circuit here where this yellow wire used to be to, and we allowed the current to go through this red wire into the meter positive terminal, out of the meter's negative terminal, and back into the yellow quick clip, and then to the remainder of the circuit. And once it hits here, it'll divide into an I2, and it'll go this way, and it'll divide into R6 and R7. Okay, so the 2 meters here now will be set up to measure VT and IT. So here is a close-up of the 2 meters, and we have VT now, And we take that reading off the power supply, but we didn't take a picture of the power supply. But we noticed that VT here, the scale selector, is on 25 volts, and so that means then that this number here represents 25, and you can see then that 20 is right on 24 there. So 24 volts for VT, and that is the voltage applied to the circuit. Now, for the current meter is on the 25 scale, and of course it's DC milliamps that we're measuring. And so if it's on the 25 scale, again, we're using this bottom scale here, and you see then that it's less than 20. It's really close to the first main division there below 20, and so we call that 19 milliamps. So remember now that 19 milliamps is IT. It is also the current through R1, and you could record that one as the current through R9. However, we did measure the current through R9 individually a bit later and did get 19. But the idea is that, of course, in that circuit, the current that flows out of the source must go back to the source. So our IT, 19 milliamps, I1, I9, both 19 milliamps. Now, lab procedure A6 then asks us to complete the measurements of voltage across current through each resistor. And when we did this in the lab, we did go ahead and measure the voltage across and the current through each resistor and completed table 6.2. The resistor measurements that we have decided to include here are for resistor 1, resistor 4, and resistor 6. And so here is the circuit set up to measure I1 and V1, even though the leads from the meter is kind of covering that up a little bit there. The idea again is that we didn't move the current meter because we were measuring IT equals I1 from the first or the previous slide. And so again, the current comes out of I1 and goes into the milliamp meter. It will go through the milliamp meter's internal circuitry, come out through the milliamp meter's negative terminal, and continue on to the rest of the circuit. So the milliamp meter is in series with I1, therefore it measures the current through I1. Now the voltmeter, however, we have moved, and you'll notice that our voltmeter here, its positive terminal now is connected through this lead to the left side of R1, and that is because the left side of R1 is closest to the positive terminal of the power supply, so that is positive for its voltage drop and positive for the connection of the meter. Now the negative terminal of our voltmeter then has been connected, and you see it goes under the table here, but it comes back up and it goes on to the right side of R1, which would be the negative side of R1 if we marked its polarity on the figure 6.1. And so the voltmeter is across R1, it will measure the voltage for resistor 1. Okay, so the close-up of the meters for I1 and V1. Now you notice then if we start with I1, I1 is on the 25 milliamp scale still. And so again now, that means 25 milliamps is the maximum measurement here, so the 25 scale. And you'll see again that that's really close to 19, might be a shade above, but we call that 19 milliamps. Now for the voltmeter, this one is a little interesting because if you look at this one now, we haven't moved to the 5 volt scale, which means the maximum measurement over here represented by full scale deflection is 5 volts. And so that means that we should use the scale directly above the mirrored line here, which ends in 5. And so you'll notice now that 4, 4.5, 4.678, that's just above 4.8 volts there, because this number right here in the middle of 4 and 5, of course, is 4.5. And you'll notice that we have included 4.42 volts in table 6.2 for that, and so that seems to be an error. And so we see now how many students picks up on that from this audio as opposed to copying the numbers out of table 6.2, and so you should record that one as 4.82 volts to be a little bit more accurate according to that meter reading. Now, the meter is connected then to show I4 and V4. And so remember that from figure 6-1, this resistor right here is R4. And so the voltmeter, its positive lead connected to the top of R4 right here, or its positive end, the negative lead from the voltmeter connected through here to the bottom end of R4, or its negative terminal. So the voltmeter across R4. For the milliammeter now, the positive terminal comes to this clip right here. And you'll notice that we took these two clips off of R4. And the idea is that, remember, we have to isolate one end of R4 so that there's nothing connected to it except for meters. And so the current that used to go through this red clip and this black clip and into R4 must now go through the ammeter and back from its negative into the resistor R4. So that current now goes through the meter before it goes into R4. And so we look at our close-up now of the meters for resistor 4. Hopefully we won't find a mistake in them this time. We start with the voltage meter now, and you'll notice we've moved the voltmeter selector switch to the 10 volt scale. It tells us that now 10 volts is the maximum measurement or full scale deflection. So we should use the very top set of numbers here to make our measurement. And so you'll notice 4 halfway, then here's 5, 6, and you'll notice that that meter needle there is approximately almost exactly halfway between 5 and 6, so we measured that as 5.5 volts. Okay, for I4, then the milliammeter is on the 10 milliamp scale now, and so again we'll go to the very top set of numbers for the scale over here. And so now again, we are between 4, 5. We're between 5 and 6 milliamps, and right almost exactly halfway between. And so we have recorded that current as 5.5 milliamps, which is interesting because that agrees a lot closer with the color-coded value if you apply Ohm's law than it do with our measured value of 1150 for R4, doesn't it? Okay, so the last set of meters that we've shown you is the measurement for I6 and V6. And so from from figure 6-1 now, this resistor at the very top here was R6. And so we have broken the circuit by taking off this blue clip right here that used to bring current from this junction into our R6, and we have connected that through this red wire here to the positive terminal of the milliammeter. So now the current must go through the milliammeter, come back out through the black lead and go into the resistor. For the voltage then, this red lead here is connected to the positive terminal of the voltmeter. The negative terminal of the voltmeter comes back to the right side of the resistor. And so think about when you connect the polarity of the voltmeter, about how you would mark the polarity of the resistor on the circuit, and it would indeed be positive on this side and negative on this side with the direction of assumed current. So now on the next slide, we show the close-up of these two meters. And we have then for I6, we are on the 10 milliamp scale. And if you look at the 10 here and the top set of numbers, 6 halfway between 6 and 8 represents 7. And so we are approximately 6.4 milliamps there, and in actual fact we recorded that as 6.5 milliamps. Okay, if we move over to the voltmeter now for V6, we are again on the 10 volt scale. So if we're using the top set of numbers, we're just above 5 there, and you'll notice that oh, I'm sorry, this number is 6 and 8. We're just above 7 there, and you'll notice that we wrote in 7.2 volts as the voltage for V6. So the rest of the measurements again can be taken from the supporting document or from table 6.2, which is on the very last slide of this presentation. Now let's move on now to part B of the procedure, and basically this is what we want you to simulate. And so I think we're going to forego the simulation of the circuit in figure 6-1. And what we're going to ask you to do now is following procedure step B1. You need to pick 4 different resistors of the 9 that were used in this experiment. So I've listed them out here. They are found in the materials and equipment, or the equipment and materials required list from page 53 of the lab, and the non-resistors then in ascending order: 270 ohms, 330 ohms, and so on, 475, 60, 1K, 1.2K, 1.5K, 3.3K, 3.9K. So there's 9 different values used in figure 6-1. And we want you to pick 4 of those values and come up with a series parallel circuit which contains 4 resistors, with different values, that will draw approximately 10 milliamps from a 12-volt DC power supply. And so we gave you a 2.5% plus or minus error there, so that there's one design that will give you exactly 1200 ohms using those resistors, and there's some other designs as well. There's one where I think you can get 1210 ohms, and so that meets our plus or minus 30 ohms, right? And so if you use Ohm's law, 12 volts divided by the 10 milliamps suggests 1200 ohms. And so if we got you within plus or minus 30 ohms, I think that means that there are a few different designs that will satisfy the design specifications given. And so now, include your calculations with your submission, and then complete table 6-3 with the total resistance that you come up with. And I think that this is the circuit we're expecting you to come up with, right? A series parallel circuit that contains 4 resistors. We don't want you to put out resistors in series. We don't want you to put out resistors in parallel. And I think 1 resistor in series with 3 in parallel. I'm not sure if there's a design for that one that will satisfy the specifications, but you might be able to come up with one. There's a few that fit this format here, and well, there's at least 2, but I think there's 3 or 4 that'll fit this format here. So that's probably what you should start with. And this is a little bit of trial and error, there's no doubt about it. Try some parallel combinations for your resistors and compare that then to the list and to the 1200, and see what you can come up with. So once you come up with your design, again, I'll ask you to include your design calculations with your lab submission, and sketch the circuit according to the instructions in step B2 in the lab, and then using the multi-sim software, simulate your circuit. And so what you should do is include the 4 resistors and then connect an ohm meter, verify that you got the 1200 ohms plus or minus 30 ohms, record the value as a measured value in table 6.3, then add your 12 volt power supply, put in an ammeter to measure IT and a voltmeter to measure or show the VT measurement, and then simulate your circuit and record the the current and the voltage that your meters show in table 6.3, and then the 2 screenshots, one that shows your ohm meter with the RT measurement, and one that shows your ammeter and voltmeter with the IT and VT measurement, and include those 2 screenshots with your lab report. So for your submission now, you should include sample calculations, page 52, one type of each specific calculation that you did in the lab, Your results page, page 56, which again part of is on the next slide. Your circuit design, so your design calculations and a sketch of your circuit according to procedure B on page 55, the answers to all the questions on pages 57 and 58, and the 2 screenshots according to part B, or according to this one that again shows RT before you connected the power supply, and a second one after you connected the power supply, and meters to show VT and IT. Okay, thank you very much, and we'll move on now to the results page. And so you'll notice that again I'll mention that V1 there should have been 4.82 volts, and I don't think that we found any other mistakes in there. Some of the calculated values have been shown in table 6-1, and that's just to help keep you on track there. This one there that you'll notice, this one here, that's 2.4 milliamps, which is close to the 2.3 that we measured. I think all of them are relatively close to the ones that we measured, right? V1 at 5.4, yeah, maybe that one. See, the measurement was a bit low. 4.82 is a bit closer, and so they're off. A lot of them will be off by a little bit, I think. We got V8 included there as 4.2, and we measured 4, and so most of them should be really close. Now, so thank you. That's the end of experiment 6.